All right, today we're going to be going over related rates. So I have 29 problems here, and if you want to do them ahead, you can find that on my website. The link will be in the bio. Also, have the answers there if you just want to look at that. But if you're trying to understand, I would recommend watching the video. I'll be going through them nice and slow, helping you guys out. But what are related rates? So when we think about two rates that are related, one example could be I'm walking 2 miles per hour and you're walking 2 times faster than I am. Okay? You can think about it, but the answer is pretty intuitive. You're going to be walking 4 miles per hour. These rates are related because you're walking 2 times faster than I am. In related rates, what we're trying to do is we're trying to find similar relations between these things. For example, a circle. Our first problem is a radius and an area. These two rates are going to be related. And what we have to do is we have to figure out how they're going to be related. And we do that through calculus, derivatives, and implicit differentiation. So, let's just get into it. All right, an expanding circle. A circle's radius increases at a rate of 2 centimeters per second. Okay, so we know one rate. It's something that we know. And we'll get back to that in a second. Find the rate at which the area of the circle is changing. So this is the rate that we want to find when the radius is 5 centimeters. So now we know something. We have some sort of condition. Okay. Now the methodology that I use, the first step is going to be defining what we want to find. We want to find the rate at which the area of the circle is changing. So the change in area, we can call this dA, change in area, over the change in what? Now this isn't explicitly given, so we kind of have to think about it a little bit, but our answer is going to be time. And the reason why is because the circle's radius is going to be increasing in terms of time at 2 centimeters per second. So our rate at which the area is changing is also going to be in per second, which is dt. dA over dt. This is what we want to find. Next, let's define what we know. We know a circle's radius increases at a rate of 2 centimeters per second. Okay, so change in radius, we'll write this dr, 2 centimeters per second. Per second is going to be over time, so we'll call this dr dt. We can say this is equal to 2 centimeters per second. We also know that radius equals 5 centimeters, and this is given to us in the problem. So now we have what we want to find and what we have, and we need some sort of way to relate these two things. And this one's pretty easy. It's just going to be our area of a circle equation. So our third step is going to be the equation that relates these two things. Area equals pi r squared. Our two variables are a and r, area and radius, and those are the two things that we have and what we want to have. So now we have how these variables are related, but we want to find out how their rates are related. And how can we find out how their rates are related? Well, we are going to take the derivative of this. But we're not just going to be taking the derivative. We're going to be taking the derivative with respect to time. The reason why we're taking it with respect to time is because everything that we know and that we want to know is with respect to time. So think about over dt and over dt. These are both with respect to time, so we're going to implicitly differentiate with respect to time. Okay, let's start off with the right. D over dt, with the left side of A. Okay, so let's take a quick pause and look at d over dx of x. This we know is 1. But why is it 1? And the reason why it's 1 is because we're differentiating with respect to x. When we do a problem like this, one way that I like to think about it is you take this x and you bring it out and you put it next to that d. You get dx over dx. And these cancel out, and we get 1. So dx over dx equals 1. Now let's say alternatively, we're doing d over dx in terms of y. We know that this is not 1. And why is that? Because we can put the y up there, dy over dx. These do not cancel out, and they do not equal 1. So we just leave this as dy over dx. We can do the same thing over here. We move this a, and we get dA over dt, which is not 1. dA over dt, the change in area with respect to time. Okay, now let's find the derivative of our right side with respect to time. Pi r squared. So pi is a constant. So what we want to really focus on is d over dt of r squared. And I'm actually going to write it like this. I'm going to put that r in its own parentheses. And the reason why I'm doing that is because I want you to think of this as a chain rule. R squared is our outer function, and then our r is the inner function. And for a chain rule, we do the derivative of the outer times the derivative of the inner. So our derivative of the outer, 2 times r, you bring that exponent down and then minus the 2 by 1, multiplied, and remember the derivative of the inner, which is just r, can move that r next to the d and get dr over dt. And this is, we have to multiply this by pi, and then this is the derivative of the right side. Now we can bring in dA over dt, and let me do this right here. dA over dt equals 2 pi r times dr over dt. And now we have 3 variables, and we want to find dA over dt. Luckily, we know 2 of them. We know dr over dt, if we go up, we set this equal to 2, and we know that we set r equal to 5. This is given to us in the problem. So dr over dt is 2, r is 5, and we're left with dA over dt equals 2 pi times 5 times 2. dA over dt equals 20 pi. And our units for this, centimeters squared per second. The reason why is because we're doing A over T, area is centimeters squared, and time is in seconds. And this is again given to us in the problem. A over T could also be meters squared per hours or something. So you want to make sure that you're paying attention so that you can get the units right. And this is our first problem done. All right, let's move on to our next one. A falling ladder. A 10-foot ladder is leaning against a vertical wall. The bottom of the ladder slides away from the wall at a rate of 1 foot per second. Find the rate at which the top of the ladder is sliding down the wall when the bottom of the ladder is 6 feet away from the wall. Okay, this is a lot. The first step here is going to be creating an image. A 10-foot ladder is leaning against a vertical wall. Okay, this will be our wall. A 10-foot ladder. Okay, a ladder. And this is fixed at 10 feet. The bottom of the ladder slides away from the wall at a rate of 1 foot per second. Okay, so this is moving at 1 foot per second. And we know that if the bottom is sliding, the top also must be sliding down. Okay? And the bottom of the ladder is 6 feet away from the wall. So this is 6 feet. And now, is a great time to define our variables? Well, we have a triangle. Why don't we call this x, this y, and we'll call our hypotenuse z. Okay, so y, x, and z. We know z is 10. Okay, so z equals 10. This is going to be fixed. Okay, now our first step is, what do we want to find? We want to find the rate at which the top of the ladder is sliding down the wall. Let's call this dy over dt, because we're working in terms of seconds, over seconds. Okay? 2, what do we know? Well, we know that z equals 10. That's given to us. We know that at the moment that it's moving, x equals 6. This is the instant that we want to find our rate. And we also know that the bottom of the ladder slides away from the wall at a rate of 1 foot per second. Let's call this dx over dt equals 1, because that is the rate that x is moving in the positive direction. Okay? So dx over dt equals 1. And these are going to be the 3 things that we know. Now we need some sort of equation to relate these. Well, we know that this is a right triangle. And what's special about a right triangle? Pythagorean's theorem. X squared plus y squared equals the hypotenuse squared, or z squared. And right off the bat, we can plug stuff in. Say x squared plus y squared equals 100. And that is because our hypotenuse is fixed. Okay. Now, let's implicitly differentiate with respect to t again, d over dt. And using the same method as before, we get 2x times dx over dt. So we're using the chain rule with respect to t. Then we're moving our x next to that d, so we can get dx over dt plus the same thing for y, 2y times dy over dt equals, now we have our derivative of a constant, which we know is 0. Okay. We know x, we know dx over dt, so let's plug these in. 2 times 6 times 1 plus 2 times y times dy over dt. Okay. We get 12 plus 2y dy over dt equals 0. And now we have our y and dy over dt, which is what we want to find. So we want to figure out what y is now. And we can do that, again, using Pythagorean's theorem. So x is 6 squared plus y squared equals 100, because z is 10 squared. Y squared equals 100 minus 36. Y squared equals, this is 64. And we know that y equals 8. And we can plug this in. 12 plus 2 times 8 dy over dt equals 0. Rearrange things and we get negative 12 equals 16 dy over dt. Divide both sides by 16 and we get negative 12 over 16, which is negative 3 over 4. And this, the units, feet per second. Y is in feet and t is going to be in seconds. And this is going to be our final answer. And you might be asking, well, why is it negative? And the reason is because our ladder is going downwards. Positive y is upwards, negative y is downwards. So if it's going downwards, that rate is going to be negative. So negative 3 over 4, even though it looks a little weird, checks out. Okay. Water filling a cone. Water is poured into a conical tank at a rate of 5 centimeters cubed per second. Okay, so now things are getting serious. Why don't we start off with a diagram? This is our cone. And we know that water is being poured in. This is going to be my water. And this is at a rate of 5 centimeters cubed per second. And what is this? Okay, so centimeters cubed, if something is cubed, that's going to be our volume. So rate of volume over time, dV over dt. Okay, centimeters cubed is volume. The tank has a height of 12 centimeters. Okay, and a radius of 4 centimeters. Find the rate at which the water level rises when the water is 6 centimeters deep. Okay. So this is 6. Okay, now this one is a little bit tougher. Why don't we start off with the volume of a cone? I'm just going to double check. Okay, so our volume of a cone. Okay, so now what we need is something that relates height and volume. So start with what we want to know. The rate at which the water level rises, dH over dt. Okay? 2, what do we know? And this is h because this water level is going to be the height of a smaller cone. So we'll call this a smaller cone here. And it has its own height. And we're looking at that height, the rate of change of that height. 2, what do we know? Well, we know dV over dt equals 5. We also know that h of 0, so the big cone, has a height of 12 and a base radius of 4. Find the rate at which the water level rises when the water is 6 centimeters deep. Okay. Now this one is a little tougher compared to the last ones that we've done. But we know, okay, let's say that volume equals pi r squared h over 3. This is our volume of a cone. Pi r squared h over 3. Okay, so we run into some problems if we try to take the derivative of this. And the reason why is because we get a dr over dt on the right side. And do we know what dr over dt is? We don't. We don't know what dr over dt is. So we need to find a way to change this. Change this into something that's similar that we know. And we know dv over dt, and we want to know dh over dt. So we can actually turn this r into an h. Okay, let's think about this like a triangle. Our h, then we have our r, then we have this number. But let's not worry about our hypotenuse. Let's think about how h is changing with respect to r. So h is 12 and r is 4, and that's going to be our big cone, that triangle. So this big triangle. Now, a cone, our small triangle where the water is going to be a similar triangle to this big triangle. Okay? And we know that that smaller triangle at the point we're looking for has a height of 6, which means that it has a radius of 2. And we also kind of understand that there's some sort of relationship between the two. We can say that 3r equals h. H is always going to be 3 times bigger than r. And we can plug this in. So we can change this equation by plugging in r equals h over 3 for r. That way we can get everything in terms of h and v, which is what we want because we don't know anything about r. We want to learn about everything in terms of h and v because we don't have a rate for r. So we get v equals pi times h over 3 squared h over 3. And this we can turn into v equals pi h cubed over 27. We're taking out the over 3 squared. That turns into over 9, and we're multiplying that to the bottom. So we get 3 times 9 is 27 on the bottom. And now we have something a lot more manageable. V equals pi h to the third over 27. And we can differentiate it with respect to time again. Most of what you're going to be doing is with respect to time. There will be some times where it's not, but definitely watch out. So here, again, we know that everything is over seconds, so that gives us the clue that it's in terms of time. When we differentiate our left side, we get dv over dt. Remember, just pulling out the v, putting it in there, equals, okay, let's take out our constant, because we know that that's not just going to disappear because it's not alone. And then let's find out what d over dt of h to the 3 is. Our first step, the derivative of the outside in our chain rule, and the derivative of the inside. We multiply it by dh over dt times 3h squared dh over dt. We know h is 6 at the exact moment that we're trying to find it. And we know dh over dt. Sorry, we don't know dh over dt, but we know dv over dt is 5. So we can plug these in. 5 equals, I'm going to take our 3 and our 27, and 3 divided by 27 is 1 over 9. So you can say pi over 9 times h is 6 squared, dh over dt. Okay. Now, we can kind of cancel stuff out and bring things over. So we get 9 times 5 over pi times 6 squared equals dh over dt. And this turns into 45 over 36 pi equals dh over dt. And this is in terms of, we are looking at centimeters per second, because h is in terms of centimeters, t is in terms of seconds. And this is our third problem done. Okay. A growing square. Oh, we're back to hopefully an easier one now. A square's side length increases at 3 centimeters per second. Find the rate at which the square's area is increasing when the side length is 10. Oh, This one, hopefully, you can think about it and kind of understand how to do it. So, a square, every side length is equal. That's going to be the most important thing here. They kind of trick you. They say a square side length increases, but really it's all of the square sides are increasing by that same amount. Okay, let's look at what we want to find. We want to find the rate at which the square's area is increasing. dA over dt. Again, we're working in dt because we're doing centimeters per second. 2. What do we know? Well, we know dl over dt equals 3. Okay, the side length increases at a rate of 3 centimeters per second. And we also know that at the moment we're looking for L equals 10. Okay. Now what is our equation to relate these two things? Well, A equals L squared. Just the area of a square. And we differentiate this with respect to time. Bring the A out, dA over dt. And then, like we've been doing, you can look back if you're still confused about this part, but I'm just going to go through it. 2L times dL over dt. We know dL over dt, and we know L. dA over dt equals 2 times 10 times 3. Okay, that's just from plugging dL over dt and L into our problem. dA over dt equals 20 times 3, 60. Our units are centimeters squared, because it's area, over seconds, the time. All right, looks good. Rising hot air balloon. A hot air balloon is rising vertically at 2 meters per second. Okay, this one looks long, so I'm just going to go ahead and start drawing it out. Our hot air balloon, I'm just going to make a circle. And it's rising at 2 meters per second. And is directly above a moving bicycle. Okay, so this is our bicycle. And that is moving horizontally at 4 meters per second. Find the rate at which the distance between the balloon and bicycle is changing when the balloon is 20 meters above the ground and the bicycle is 15 meters away horizontally. Okay, so this is actually not directly under. I'm going to call this some sort of triangle. We know that this is what we're trying to find. We'll call this Z. We'll call our horizontal distance X and our vertical distance Y, just to stay consistent with previous problems. Okay. Balloon is 20 meters above the ground. We know Y equals 20 meters. And we know X is 15 meters away horizontally, so X equals 15 meters. And now, once again, we have a right triangle with Y, X, and Z. Okay. 1. What do we want to find? The distance between the balloon and the bicycle is changing. So that's going to be Z over, again, we're working with time, meters per second, dz over dt is what we want to find. 2, what do we know? We know y equals 20, x equals 15, and let's just go ahead and find z right now. So y squared plus x squared equals z squared. 20 squared plus 15 squared equals equals z squared. And I'm going to use a calculator for this one. And I got z equals 25. So I just kind of took the square root of both sides, and I got z equals 25. And this is meters. So we know z equals 25. And we also know dx over dt and dy over dt. So we have 5 things that we know, really. dy over dt equals 2. The hot air balloon is rising at a rate of 2. dx over dt equals, well, it equals 4, because that's how fast the bike is moving horizontally. All right. Three. What is the equation that relates these things? Well, we've seen it already. Y squared plus x squared equals z squared. Now we differentiate this with respect to time. D over dt of y squared plus x squared equals z squared. And we get 2y dy over dt plus 2x dx over dt equals 2z dz over dt. Okay. Now, you might be wondering, why isn't this just constant? It was in the other problem, and the reason why is because z is not constant. Z is always changing. A ladder, that z is always going to be the same, but when it's just the distance between two moving things, that's going to become bigger and bigger. And so we can't just make it 0. We have to make it some sort of number. Now we can plug everything in. Y equals 20. 2 times 20 dy over dt equals 2, plus 2 times x is 15, dx over dt, 4, equals 2 times, we know z is 25, times dz over dt. Okay. 40 times 2, 80, plus 2 times 15 is 30, times 4, 120, equals 50 dz over dt. 200 equals 50 dz over dt, and dz over dt equals 4 meters per second. Meters, right? Yes, meters per second. So z is not an area, so it's just going to be meters. And then we're over seconds. So dz over dt equals 4 meters per second. Okay. Increasing diagonal of a rectangle. A rectangle's length increases at 1 centimeter per second, and its width decreases at 0.5. All right. Length and width, and this is increasing at 1 centimeters per second, and the width is decreasing at 0.5 centimeters per second. The length is 8 centimeters, and the width is 6. Find the rate at which the diagonal is changing. Okay, let's call this z. So we have width as w, length as l, and the diagonal as z. Okay, 1, what do we want to find? Well, we're working over seconds again, and we want to find the diagonal, which we called z, dz over dt. And you can call it whatever you want. You can call it d. Oh no, don't call it the diagonal d, because then you'd have dd over dt. But you can call it capital D, maybe. Whatever you want, whatever you feel comfortable with. I'm just calling it this for consistency. Okay, 2. What do we know? L equals 8, W equals 6, dl over dt equals 1, because it's increasing by 1, dw over dt equals negative 1 over 2. And why is it negative? Well, because w is getting smaller, and when something gets smaller, the derivative is negative. So dw over dt is negative 1 over 2. We also know that at this exact moment, z squared equals 8 squared plus 6 squared, and we're going to get z equals 10. So z squared equals 100, z equals 10, z equals 10. Now we have our unknown and all of our knowns. We can relate these two, and this one, once again, like, we don't even need to worry about it being a rectangle. We can just think about this as a triangle. We know that this is getting bigger, and this distance is getting smaller, and we're trying to find z. So let's write that as w squared plus L squared equals Z squared. Now we differentiate it in terms of time, because we're trying to find dz over dt time, and we get 2w times dw over dt plus 2l times dl over dt equals 2z times dz over dt. Now we can plug in what we know. W equals 6, so 2 times 6 times negative 1 over 2 plus 2 times L is 8 times 1, dl over dt is 1, equals 2 times 10 times dz over dt. Okay. Negative 6 plus 16 equals 20. dz over dt, 10 equals 20, dz over dt, and dz over dt equals 1 over 2, or in terms of centimeters per second, centimeters per second. And that is the final answer. Again, z is centimeters, t is seconds, so we can kind of bring this directly in for our units. Z over t, centimeters divided by seconds. cm over s. Airplane and radar. An airplane flies horizontally at a constant speed of 300 meters per second. Let's draw this out. 300 meters per second. Oh, that's pretty fast. It passes directly over a radar station at a height of 4,000 meters per second. Okay, this is our radar station. And this time, it's directly over, and this is 4,000 meters. Find the rate at which the distance is increasing. When the airplane is 5,000 meters from the radar station. Okay. We're going to move this. And we're going to say that this is 5,000 meters. Okay. Y, X, and Z. We know, or we want to find dz over dt. Okay. The distance between the radar station and the plane. We know dx over dt equals 300, positive 300, because it's going in the positive x direction. we know y equals 4,000, z equals 5,000, and we can say x equals, unless my memory is failing me, 3,000. Double check this. 4,000 squared plus 3,000 squared, and you take the derivative, or the square root of that, and you get 5,000. So x is 3,000. Once again, we have a right triangle. We can say that z squared equals y squared plus x squared. We're going to differentiate this in terms of time, once again, because we're over seconds. Get 2z dz over dt equals 2y dy over dt plus 2x dx over dt. Okay, now we plug stuff in. 2 times z is 5,000. dz is what we want to find, so we just leave this. Equals 2y is 4,000 times dy over dt plus 2 times 3,000 times dx over dt. Okay, which is, we know, is 300. Okay, so now we have two unknowns, dy over dt and dz over dt. But we can actually deduce dy over dt because our plane is flying only horizontally. It's not going upwards, which means y doesn't change. So that makes dy over dt equal to 0. So we can cross all of this out. And we get 10,000 dz over dt equals 6,000 times 300. We can do dz over dt equals, well, 6,000 divided by 10,000. It's just 6 over 10 times 300. We can get rid of a 0 from the top and the bottom. And we get dz over dt equals 6 times 30, 500 meters per second. All right. And that is our final answer. 500. Nope, that is very wrong. 180 meters per second. 6 times 3, 18. Add a 0, 180. Okay. Draining tank. Water drains from a cylindrical tank at a rate of 20 liters per minute. The tank has a radius of 3 meters. How fast is the water level in the tank dropping when the water is 4 meters deep? Okay, cylindrical tank. Let's go ahead and draw that out. The tank has a radius of 3, so r equals 3. We'll call this little r. And we want to find the level in the tank, how fast it's dropping when the water is 4 meters deep. Okay, now, if you think about this, does the water level actually matter here? And the answer should be no, because no matter when you look at it, it should be filling up at the same rate in terms of height. But let's talk about what we want to know, and that is how fast is the water level in the tank dropping? dH over dt. Okay? And this time, rather than seconds, we're working with minutes. So that is exciting. 2, what do we know? Water drains from a cylindrical tank at a rate of 20 liters per minute. Okay? Liters are volume, minute is time, and it's draining, which means it's going to be a negative rate of change because that amount is getting less. We know that R equals 3 and H equals 4. Okay, what is a equation that relates height, volume, and radius and a cylinder? Well, we can do the volume of a cylinder, which is just going to be the area of a circle multiplied by the height. Okay, so V equals pi r squared h. And right off the bat, we know a few things. One is we know that R is constant, so no matter where you look at it, R is always going to be 3, so we can just plug that in now. 3, 9 pi, because we square it, h. Okay. Now we have everything in terms of V and H, and those are things that we know. Differentiate this with respect to time. d over dt, dv over dt equals 9 pi times dH over dt. And we know dv over dt is negative 20. And notice how this doesn't rely on h. Our related rates don't rely on h. At the beginning, we made a guess that it wasn't going to depend on the height, and here we can see this reflected in the equation. It's not dependent on the height at all. dv over dt is negative 20 equals 9 pi times dH over dt, and we get dH over dt equals negative 20 over 9 pi. Okay, and this is going to be meters per minute. Okay, meters per minute. Our H is in terms of meters. Our T is in terms of minutes now. And the problem is asking how fast is the water level in the tank dropping? Okay, well, how fast is it dropping? If it's dropping a negative rate, that'll mean that it's actually filling up because it'll do the opposite. So when you answer this with words, what you want to make the negative 20 over 9 pi positive because that's the rate that it's dropping. Okay, the rate of change of the height is negative, which means that when it's dropping, we set that to a positive rate. So we would say that at when the height is 4, the radius is dropping at 20 over 9 pi meters per minute. Okay. I hope this is starting to come along. Let's do the expanding balloon problem now. Air is being pumped into a spherical balloon at a rate of 50 centimeters cubed per second. Find the rate at which the radius of the balloon increases when the radius is 5 centimeters. Okay. Spherical balloon, which has an increasing radius, but we want to find it when r equals 5. Okay, we also know that air is being pumped into it at a rate of 50 centimeters cubed per second. Centimeters cubed is going to be volume, seconds is going to be time. So we know that dv over dt is going to be 50. But let's start with finding what we want to find, the rate at which the radius of the balloon increases. Rate of change of the radius over time, dr over dt. Now we can get to what we know, r equals 5, dv over dt equals 50. Centimeters cubed is volume, and seconds is time. Okay, 3. What is a equation that relates these? Well, we can use the volume of a sphere, v equals 4 over 3 pi r cubed. Okay. And the only two variables here are v and r, and we want dr over t, and we have dv over dt, so we don't need to do any more manipulation. We can just take the derivative with respect to time. Let's just take the derivative with respect to time. Okay, we get dv over dt equals, okay, 4 over 3 pi is our constant, and when we take d over dt of r to the cubed, remember, chain rule the outside, 3r squared, times the derivative of the inside, we can move that r to the top and get dr over dt. And remember that if we are differentiating in terms of r, so d over dr, we would get dr over dr, which is equal to 1. But since we're differentiating in terms of t, it's not going to be equal to 1, and we just leave it like that. So times 3r squared times dr over dt, and we can see that our 3's cancel out, which is nice. Okay, now we're left with dv over dt equals 4 pi r squared dr over dt. And we know r and dr over dt. So we know that r equals 5, which means the r squared is 25. And we know, we want to find dr over dt, and we know dv over dt. So we know dv over dt equals 50. And after we manipulate this a little bit, we get 2 over 4 pi, which is 1 over 2 pi, equals dr over dt. And this is our units. I'll put in the units. We are talking about centimeters and seconds. cm per second. Okay. I hope everything is making sense, and I'm going to cut it off for today. But we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. I don't know if I counted right, but we have a lot more problems to go. So I am going to make a part 2 and probably a part 3 as well. We were able to get through 9 out of 29, so this will probably be a 3-part series, so stay tuned for that. And you can find this on my website, which is linked in the bio. And I'll include all of the answers once I release the 3-part series. So if you're looking for that, it won't be there quite yet. But I will go ahead and put this problem set out there so you guys can work on that on your own. And thank you for tuning in. I'll see you guys for part 2 and part 3. Hopefully you don't need it. Hopefully you guys are good enough that everything is making sense, and you don't even need to watch that. But if you want extra practice, go ahead, try the rest of these, and then check your answers when they come out. Thank you guys.